Alright, let's look at a couple of applications using quadratic equations. It says the height in feet reached by a baseball or by a batted baseball after t seconds is given by this equation. So the height is h and t is time in seconds. So let's keep track of that. H is the height and t is the time in seconds. This is in feet, this is in seconds. And the graph of y equals h of t, or y equals this, or the function notation h of t equals that, is given. Interpret the y-intercept. Well, remember the y-intercept is when the graph crosses the y-axis, and that's right there, the y-intercept. So remember, y-intercept we always get by making x 0. Because on my graph it's hard to see, but it looks like it's a little bit above 0. But I can get it from, in this case it'll be t equals 0. I can get it from y equals or h of 0, which makes everything else drop, and the only thing I have left is the 2. So y or h is equal to, at 0, 2 feet, which is what my graph shows, but it's hard to tell. So t is 2, and I'm sorry, h is 2 and t is 0. So at 0 seconds, ball is 2 feet above ground. In other words, right when it was hit. Right when it was batted, the ball was 2 feet above the ground. That's what the y-intercept tells me. Part B says, use the graph to estimate when the baseball is 70 feet in the air. Well, this is the height, and 70 feet is right here, so when is the ball 70 feet up in the air? It looks like maybe around 2 seconds. Based on the graph, it's 70 feet up. It looks like maybe 270 would be an ordered pair here. So when is the ball above the ground 70 feet? Maybe around 2 seconds would be our guess by looking at the graph. Part C says, solve part B symbolically or algebraically. So 80 or 70 feet is the h, and the question is when, which means what is the t value. So I go back to my original equation, I make the h 70, the height, and then that leaves me with figuring out what the t should be. So notice this is a quadratic equation, and I'm going to set it equal to 0. That's going to give me 0. Let's get some more space here. 0 equals negative 16t squared plus 66t minus 68. So this is a quadratic equation, and I could factor out a GCF out of this, or since it's an equation, whatever I divide the right side by, I can divide the left side by as well. And I see that they're all divisible by 2, so I'm just going to go ahead and divide everything by 2. And since this is a negative and I would rather have my leading coefficient be positive, I'm going to divide everybody by negative 2 again, since this is an equation. If it was just an expression, I couldn't do this. So I divide everybody by a negative 2 to make the number smaller and the leading coefficient positive. 8t squared minus 33t plus, it looks like 34. Now in order to factor this, it looks like the GCF, there's no GCF to pull out, so I'm going to have to move, if I'm using the WOW method, the 8 back up and get t squared minus 33t plus 272, and hope that this is factorable. So now I need a product of 272 and a sum of negative 33, and I have to go through all the factors of 272, kind of a big number, to come up with two of them that add to a negative 33, and since this is a positive and this is a negative, both of them have to be negative to add to be staying a negative number and multiply to become a positive number. So the two numbers that work are 17 and 16, because if I'm looking at 272 and adding to a negative 33, if I do negative 17 times negative 16, I get that product of positive 272. And if I add those guys, I get the negative 33 also. But since I had multiplied originally by an 8, I have to divide these guys by an 8 now. And that's going to give me this one that reduces, so that's going to be t minus 2. This guy doesn't reduce, so I move it up, 8t minus 17. So basically this is the factored version of this right here. Now I'm finally able to pop out my solutions. That's going to be 8t minus 17 equals 0, t minus 2 equals 0. So I actually have two solutions. It looks like I have t equals 17 over 8, or t equals 2. So what this tells me is that 2 seconds later, ball was 70 feet above ground, and also 2.125 seconds later, the ball was 70 feet above the ground. So when I did it symbolically, let's go back to the picture, I got two different answers, whereas visually or graphically, I just got that the ball was above the ground 2 seconds later. And remember, I guessed, I said around 2 seconds later, it's 70 feet above the ground. So it's visually, it's hard to tell, but apparently what happens is the ball goes up, and then 2 seconds later, it's 70 feet high, and then it goes a little bit higher, and then 0.125 seconds later, it's on its way down, and it's again around 70 feet above the ground. So it's hard to see it graphically. Part D says, why are symbolic solutions important? Because they are more accurate. Sometimes, visually, you guesstimate, but if you actually go do it symbolically, it sheds more light. Like here, I only got one answer visually by looking at the graph, but when I did it symbolically and I set it equal to the 70 feet high above the ground, I ended up with two different times when the ball is actually 70 feet above the ground. So if you zoom in, basically what happens is right here at 2 seconds, the ball is 70 feet, and then it goes up and comes back down, and 2.125 seconds later, the ball is still 70 feet above the ground. So there's really a higher point in between these two times that the ball goes up above. Okay, next example says a 5-foot wide sidewalk around a rectangular swimming pool has a total area of 900 square feet.